Good morning. I am Mrs. A. AROKIAMARY, Assistant Professor, PG and Research Department of Mathematics, St. Joseph's College of Arts and Science, Autonomous, Cuddalore. Now I am going to explain an important theorem in complex analysis, that is Hadamard's theorem. It relates the genus and order of entire function. Statement of the theorem is: the genus and the order of an entire function satisfy the double inequality h less than or equal to lambda less than or equal to h plus 1. That is, the order lies between genus, where genus is an integer, genus plus 1. Now let us see the proof. Let f of z be an entire function and denote its zeros by a1, a2, etc. an. Let f of 0 is not equal to 0. That is, 0 is not 0 of the entire function f of z. And let f of z be of finite genus h. By Weierstrass factorization theorem, we can write f of z as e power g of z into z power m into the product 1 minus z by an e power z by an plus 1 by 2 z by an whole square plus etc. plus 1 by h z by an power h. Since z equal to 0 is not a 0, we omit the term z power m. Now the exponential factor is of order less than or equal to h plus 1. And the order of the product cannot exceed the order of both the factors. Hence, it is sufficient to show that the canonical product f of z is of order less than or equal to h plus 1. The convergence of canonical product implies summation 1 by modulus of an power h plus 1 is less than infinity. It is by the definition of genus. Now we take the individual factor of this product as EH of Z by AM. That is EH of, and we denote Z by AN as U. So EH of U as 1 minus U into e power U plus 1 by 2 U square plus etc. plus U power H by H. Okay. Now when you substitute H equal to 0, we will get e power 0. So E naught of U is 1 minus U. Now we are going to prove two inequalities for all U and for all H. First inequality is this: log modulus of EH of U less than or equal to 2H plus 1 into modulus of U power H plus 1 for all U. First let us consider modulus of U less than 1 and H is greater than or equal to 1. EH of U is e power, we can write any factor as e power log. So we write e power log of 1 minus U, e power U plus U square by 2 plus etc. U power H by H. Now log 1 minus U, we know, minus U square by 2 etc. minus U power H by H. and we add this e power, both are e power, so we add this power terms. Up to u power h by h gets cancelled and we get e power minus of u power h plus 1 by h plus 1 plus u power h plus 2 by h plus 2 plus etc. Take modulus on both sides. Modulus of EH of u is modulus of e power minus of u power h plus 1 by h plus 1 plus u power h plus 2 by h plus 2 etc. Now when we take the modulus to the power, this becomes less than or equal to, so less than or equal to e power modulus of u power h plus 1 by h plus 1 plus u power h plus 2 by h plus 2 plus etc. Take log on both sides. Right side log and e gets cancelled and we get modulus of u power h plus 1 by h plus 1 plus modulus of u power h plus 2 by h plus 2 plus etc. Now take modulus of u power h plus 1 outside, and we know that h plus 2 is greater than h plus 1, so 1 by h plus 2 is less than 1 by h plus 1. For calculation's sake, we take all the denominator as h plus 1 because all the denominators are less than 1 by h plus 1. So less than or equal to mod u power h plus 1 by h plus 1 into 1 plus mod u square etc. By using binomial 1 minus x whole power minus 1 equal to 1 plus x square etc. We can write this as 1 minus mod u power minus 1. And 1 minus mod u, this term, okay, is greater than 0 because mod u is less than 1. 1 minus mod u is greater than 0. So we can bring this 1 minus mod u to left side. 1 minus mod u into log modulus of EH of u less than or equal to mod u power h plus 1 by h plus 1. Since h plus 1 is greater than 1, 1 by h plus 1 is less than 1, so we can write this as it is modulus of u power h plus 1. Now EH of this we take it as inequality 2. EH of u is 1 minus u into e power u plus u square by 2 etc. u power h by h. That is 1 minus u into e power u plus u square by 2 etc. into e power u power h by h. We can write 1 minus u into e power up to this term can be written as EH minus 1 of u. So EH minus 1 of u into e power u power h by h. That is, we can write the modulus of EH of u as modulus of EH minus 1 into e power u power h by h. It's less than or equal to modulus of EH minus 1 into e power modulus of u power h by h. This modulus we are taking to the power, so we get less than or equal to symbol. Now take log on both sides. So log modulus of EH of u is less than or equal to log EH minus 1 plus mod u power h by h. That is, log EH of u is less than or equal to log EH minus 1 into modulus of u plus modulus of u power h. We can omit this h because we have less than or equal to symbol. Thus we take it as inequality 3. Multiply this inequality by modulus of u, then we get inequality 4. Now we add inequality 2 and 4. 2 and 4. Here we have 1 minus mod u, there we have modulus of log EH of u. So we adding these two, we get modulus of u log EH of u plus 1 minus mod u of log EH of u less than or equal to, right side also we add both the terms, and we get this minus mod u log EH of u and plus mod u gets cancelled. So we get log modulus of EH of u less than or equal to modulus of u into log EH minus 1 of u plus twice we get this term, twice modulus of u power h plus 1. This we take it as 5. And this is valid for all h greater than or equal to 1 and for all modulus of u less than 1. Now let us take modulus of u greater than or equal to 1. And suppose that modulus of EH minus 1 of u greater than or equal to 1. Then we take log on this inequality. We get log modulus of EH minus 1 of u is greater than or equal to log 1, and we know the value of log 1 is 0. That is modulus of u into log EH minus 1 of u greater than or equal to log EH minus 1 of u, because mod u is greater than 1. And using 3, inequality 3, okay, we can write log modulus of EH of u less than or equal to log modulus of EH minus 1 of u plus mod u power h, which is less than or equal to, using this, modulus of u into log EH minus 1 of u plus modulus of u power h into modulus of u, because modulus of u is greater than 1, we can use this. It is modulus of u into log EH minus 1 of u. Instead of 1 we can write 2, because we use less than or equal to symbol, modulus of u power h plus 1. Now this is same as inequality 5. So inequality 5 is true for modulus of u greater than or equal to 1. Okay. Now let us take modulus of EH minus 1 of u less than 1. If it is less than 1, taking log, we get less than 0. So we can write less than or equal to 0 plus modulus of u power h. That is less than or equal to mod u power h into mod u, because mod u is greater than or equal to 1. That is we get, and again we can write multiply by 2. 2 less than 2 into modulus of u power h plus 1. Since it is any integer, we can write, instead of 2 we can write 2h plus 1 into modulus of u power h plus 1, which is nothing but inequality 1. Thus for h greater than or equal to 1 and for arbitrary u, either inequality 5 or 1 is true. Now we are going to validate inequality 1. That is, we are going to prove inequality 1 is true for all h. Let us prove this by induction. That is, E naught of u is 1 minus u. Take modulus. Modulus of A naught of u is modulus of 1 minus u, which is less than or equal to 1 plus mod u by triangle inequality. Take log. Log modulus of A naught of u is less than or equal to log modulus 1 plus mod u, which is less than or equal to mod u by taking the first term in log, which is nothing but inequality 1 for h equal to 0 and for all u. So inequality 1 is true for h equal to 0. Assume that the inequality 1 is true for h minus 1, where h is greater than or equal to 1. That is, log EH of u is less than or equal to modulus of u into log e h minus 1 of u plus twice modulus of u power h plus 1. That is less than or, that is we can apply inequality 1 for log e h minus 1 of u. That is modulus of u into 2h plus 1 into modulus of u power h plus twice modulus of u power h plus 1. Less than or equal to 2h plus 1 into modulus of u power h plus 1, which is nothing but inequality 1. Therefore, the result holds for next higher index h. Also, we have proved for h equal to 0. So, by induction, it is true for all values of h and for arbitrary u. Now, let us consider the canonical product P of z, with this product n varies from 1 to infinity E h of z by a. Take modulus on both sides. Modulus of P of z is product modulus. Just take log modulus, take log on the product, we get summation log a h of z by a. Now we use inequality 1, so we get less than or equal to 2h plus 1 modulus of z by a in power h plus 1. Or we can write modulus of z power h plus 1 by modulus of a in power h plus 1. P of z is of utmost order is h plus 1. So, order lambda is less than or equal to h plus 1. That is, one side of the inequality is true. That is, right side inequality we have proved. Next one, to prove the other side, that is to prove h is less than or equal to lambda. Then we know that h plus 1 is greater than lambda, and we have to prove this, we have to prove summation 1 by modulus of a n per h plus 1 is convergent. By definition of genus, if this is convergent only, the genus can be h, where h is as given. Jensen's formula is needed to prove this. What is Jensen's formula? In Jensen's formula, we replace 2 row in place of row. We can find the upper bound of gamma of rho. That is, log modulus of f of 0 is minus summation I varies from 1 to n log 2 rho by modulus of a plus 1 by 2 pi interval 0 to 2 pi log of modulus of f of 2 rho e power I theta d theta, where summation extends over all zeros inside modulus of z equal to 2 rho. That is, all the zeros a1 etc. an are inside modulus of z equal to 2 rho. Log modulus of f of 0 is, we split this summation as two summations, summation 1 and summation 2. And summation 2 stands for the summation with the terms modulus of a less than or equal to rho. And summation 1 is for rho less than modulus of ai less than or equal to rho. Therefore, we can write this as 1 by 2 pi interval 0 to 2 pi as summation 1 plus summation 2. That is, we take only this term to the left side. Denote it as 7. Now, in summation 1, we know rho less than mod ai less than 2 rho. So, 2 rho by mod ai is greater than 1. When take log is greater than 0. So, summation 1 is greater than 0. So, summation 1 plus summation 2 is greater than summation 2 because summation 1 is greater than 0. It is positive. In summation 2, we know modulus of a less than or equal to rho. So, ai by rho if you take less than 1 or rho by a is greater than or equal to 1. Multiply this by 2. So we get 2 rho by ai greater than or equal to 2. Taking log 2 rho by modulus of ai is greater than or equal to log 2. Now summation over 2 is greater than or equal to summation over 2 log 2. Okay. And summation over 2, that gives us number of zeros, that is gamma of rho. So gamma of rho into log 2. Using this 8, 7 gives the integral minus log modulus of f of 0 is equal to summation over 1 plus summation over 2, which is greater than or equal to summation over 2, which is again greater than or equal to gamma of rho into log 2. Therefore, gamma of rho log 2 is less than or equal to the integral minus log modulus of f of 0. Since f of z is of finite order lambda, modulus of f of 2 rho e power I theta is less than or equal to the maximum value m of 2 rho, which is less than or equal to e power 2 rho lambda plus epsilon by 2 for sufficiently large values of rho and for arbitrary chosen epsilon. And taking log on both sides, we get log modulus of f of 2 rho e power I theta less than or equal to 2 rho power lambda plus epsilon by 2. Now, instead of log f of 2 rho e power I theta, we write 2 rho power lambda plus epsilon by 2 here. Hence, we get gamma of rho log 2 is less than or equal to 1 by 2 pi 0 2 pi 2 rho power lambda plus epsilon by 2 d theta minus log f of 0. That is less than or equal to 2 rho power lambda plus epsilon by 2 minus log modulus of f of 0, because until 0 2 pi d theta, when you integrate 2 pi gets cancelled. So gamma of rho is less than or equal to 2 rho power lambda plus epsilon by 2 divided by log 2 minus log modulus of f of 0 by log 2. Okay, we divide by log 2. That is gamma of rho into, we multiply by rho power minus of lambda plus epsilon. So here we get rho power minus lambda and rho power plus lambda gets cancelled. Rho power minus epsilon plus epsilon by 2. So rho power minus epsilon by 2. 2 power lambda plus epsilon by 2 as it is we have taken, divided by log 2 minus log f of modulus of f of 0 by log 2 into rho power lambda plus epsilon. This tends to 0 as rho tends to infinity because we have the denominator. That is gamma of rho into rho power minus of lambda plus epsilon tends to 0 as rho tends to infinity. Therefore, for large modulus of an, we know that n less than modulus of an power lambda plus epsilon. Or rewriting this, we can write modulus of an power lambda plus epsilon is greater than or equal to n. Or modulus of an is greater than or equal to n to the power 1 by lambda plus epsilon. Now raise power h plus 1. This modulus of an power h plus 1 greater than or equal to n power h plus 1 by lambda plus epsilon. Taking reciprocal, we get less than or equal to. By our choice of h, we know that h plus 1 is greater than lambda. So h plus 1 minus lambda is greater than epsilon. Or h plus 1 is lambda plus greater than lambda plus epsilon. Or we can write h plus 1 by lambda plus epsilon is greater than 1. So this is of the form summation 1 by n power p, where p is greater than 1. Hence it is convergent. By comparison test, we can say summation 1 by modulus of an power h plus 1 is convergent. And therefore we can write f of z as f of z equal to e power g of z product, where g of z is entire function. It remains to prove that g of z is polynomial of degree less than or equal to h. For this we take Poisson-Jensen's formula. we write Poisson-Jenkins formula. Apply the operator dou by dou x minus I into dou by dou y on both sides. That is, we are differentiating. So we get f dash of z by f of z equal to summation n varies from 1 to gamma of rho an by rho square minus an z plus 1 by z minus an plus integral 2 rho e power I theta by rho e power I theta minus z whole square into log of this. Differentiating again h times with respect to z, we get delta per h f dash of z by f of z. As applying nth derivative formula, we get this. As rho tends to infinity, the integral tends to 0. And first term also tends to 0 as modulus of an is less than or equal to rho. So we get del par h f dash of z by f of z as minus summation h factorial by is an minus z par h plus 1. Now we take the entire function, we take log modulus f of z and differentiate, again differentiate h times. Now equate or compare 10 and 11. When we compare 10 and 11, we get gh plus 1 of z is 0. That means g of z is polynomial of degree less than or equal to h. Thus, h is genus of the entire function. That is, h less than or equal to lambda. Thus, we get h less than or equal to lambda less than or equal to h plus 1. Hence the theorem. Hope you have understood.